The nearest star to our Sun is 4.24 light-years away, and that number sounds manageable until you convert it into something your brain can actually process. 4 light-years, a small gap on any map of the galaxy, a trivial distance by cosmic standards. But light-years are not miles, and the moment you start converting, the number becomes something different, something that stops the conversation cold. The nearest star is roughly 25 trillion miles from Earth. 25 trillion. And if you sent the fastest spacecraft humanity has ever built toward that star today, it would arrive sometime around the year 8600. That is the problem. Not that we haven't tried hard enough, or spent enough money, or dreamed big enough. The problem is that the gap between stars is a different category of distance from anything our technology was built to cross. We have spacecraft that have left our solar system. We have telescopes that can study the atmospheres of planets orbiting other stars. We have mapped the surface features of Pluto from 4 billion miles away. None of it moves us 1 inch closer to actually traveling to another star. The tools that let us see across interstellar distances are not the tools that would let us go there. Those tools don't exist yet. And the question of whether they can ever exist is more uncertain than most people realize. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Here is what makes this different from other hard engineering problems. When engineers in the 1950s looked at the challenge of landing on the moon, the physics was understood. The math was difficult and the engineering was brutal, but the path was visible. You could draw a line from where you were to where you needed to be. Interstellar travel doesn't work that way. Every serious propulsion concept either gets a spacecraft to the nearest star in thousands of years or requires physics we haven't done. There is no middle option, sitting quietly in some laboratory waiting to be funded. The gap is not an engineering gap. It is something closer to a wall, and no one has found the door. Voyager 1 is the farthest human-made object from Earth. Launched in 1977, it has been traveling for nearly 5 decades and is now roughly 15 billion miles away. That sounds vast. It is genuinely remarkable, and it represents less than 0.1% of the distance to the nearest star. At Voyager's current speed, reaching Alpha Centauri would take approximately 70,000 years. The Parker Solar Probe, the fastest spacecraft we have ever built, reaches speeds close to 450,000 miles per hour near the Sun. That speed is breathtaking by any human standard. It would still take that probe more than 6,000 years to reach the Alpha Centauri system. We are not close to solving this. We are not on the edge of a breakthrough. We are standing at the base of a wall with no idea how tall it is. What this series will cover is the full shape of that wall, the fastest things we have ever built, and why they fall short by orders of magnitude. The nuclear concepts that come closest to bridging the gap, and what they would actually require to build. The theories that might work in principle, light sails, fusion engines, laser arrays, and the specific physical and engineering barriers each one runs into. The proposals that step outside conventional propulsion entirely, into warp drives and wormholes, where the math permits something strange and the materials do not exist, and the human problems layered on top of all of it. The radiation that permeates deep space, the effects of decades in microgravity, the the psychological reality of a journey that severs every connection a person has. The goal is not to dismiss the idea of interstellar travel. It is to understand precisely what it would actually take. Because the honest answer is more interesting than either the optimistic version or the cynical one. Some of the barriers may fall, some may not. Some are engineering problems of extraordinary difficulty, and some are written into the structure of the universe at a level that no engineering reaches. Every serious attempt to answer the question of interstellar travel eventually arrives at the same place. A wall made not of engineering problems, but of physics. And the question is whether that wall has a door or whether it goes on forever. To get your head around what 25 trillion miles actually means, you have to start somewhere smaller and work outward, because there is no direct way to grasp a number that large. Start with the Earth and the Sun. The distance between them is roughly 93 million miles. That already sounds enormous. A commercial jet flying non-stop at cruising speed would take about 20 years to cover it. Light covers it in about 8 minutes. For most of human history, the sun was simply the sky, something overhead, unknowably far, beyond any scale a person could actually feel. And yet, by the standards of interstellar space, 93 million miles is nothing. It is a rounding error. It is the distance you walk before the real journey even begins. Here is a way to hold both numbers in your head at once. Imagine shrinking the solar system down so that the distance from the Earth to the Sun equals exactly 1 meter. A single meter, the length of a desk. At that scale, the entire Earth-Sun gap fits on a tabletop. Now ask where Alpha Centauri sits on that same model. The answer is 276 kilometers away. Not 276 meters, kilometers. At the scale where the Earth and Sun are a meter apart, the nearest star system is roughly the distance from one major city to another. Paris to Lyon, Los Angeles to Las Vegas. You could put our entire solar system on your kitchen counter, and the nearest star would still be over the horizon, hours away by car. This is the scale problem. It is not that space is big. You already knew that. It is that the gap between stars is big in a fundamentally different way than anything else humans have ever tried to cross. Oceans are big. Continents are wide. The distance to the moon seemed impossible until it wasn't. These are distances that, with enough engineering and enough will, human beings could traverse. The distance to even the nearest star sits in a different category entirely. Nothing we have built, nothing we have ever moved through space, has come close to crossing a gap this large. Consider Voyager 1. It was launched in 1977, and it is the farthest object humanity has ever sent into space. It spent decades accelerating on gravitational assists past Jupiter and Saturn, and it has been traveling outward ever since. After nearly 37 years of continuous flight, it finally crossed the boundary of the heliosphere, the outermost edge of our sun's sphere of influence, and entered true interstellar space. That was around 2012. As of now, Voyager 1 sits roughly 15 billion miles from Earth. That number sounds staggering. It is staggering, and it represents a tiny fraction of the distance to the nearest star. Alpha Centauri is approximately 25 trillion miles away, not 25 billion. Trillion. Voyager 1, traveling at about 38,000 miles per hour, would need somewhere in the range of 70,000 years to cover that distance, not 70,000 days. not 70,000 months, 70,000 years. Agriculture is roughly 12,000 years old. Written language has existed for perhaps 5,000 years. The entire arc of recorded human civilization could play out 6 times over, back to back, and Voyager still wouldn't be there. And here is the detail that makes it stranger still. Alpha Centauri is not just a single destination, it is a triple star system. The 2 brightest members, Alpha Centauri A and Alpha Centauri B, orbit each other in a slow gravitational dance, separated by a distance roughly equal to the span between our Sun and Saturn. They are close enough that from Earth they appear as one star, the 3rd brightest in the night sky. Orbiting much farther out is a red dwarf called Proxima Centauri, and Proxima is the one that matters most for this conversation. It is the closest of the 3 to our solar system. Its distance is 4.24 light-years. That works out to roughly 25 trillion miles, for a light-year of roughly 6 trillion miles, multiplied by 4 and change. This is our nearest stellar neighbor. These are the stars that would anchor any serious conversation about where an interstellar mission might eventually go. The 25 trillion mile figure in the title of this video represents about 2.6 light-years. That is actually less than the distance to Proxima Centauri. A probe that covered 25 trillion miles would not yet have arrived at the nearest star. It would still be in the gap, still crossing open interstellar space with no destination in sight. And yet, 25 trillion miles is a number that would take our fastest spacecraft thousands of years to reach. It is a number with no useful analogy in human experience, no equivalent journey, no reference point we can genuinely feel rather than simply recite. The rest of the galaxy dwarfs even this. Proxima Centauri is 4.24 light-years away. The galactic center is about 26,000 light-years away. The Milky Way itself spans roughly 100,000 light-years across. The nearest large galaxy, Andromeda, sits 2.5 million light-years distant. The numbers keep compounding into something the human mind simply cannot process as distance. They become abstract, almost meaningless, the way very large financial figures stop feeling real at a certain point. But the gap to Proxima Centauri, just 4.24 light-years, just our nearest neighbor, is already more than enough to illustrate the problem. You don't need to consider the whole galaxy. You only need to consider the closest thing to us outside our own solar system. And already the scale of the challenge becomes almost paralyzing. And Proxima Centauri, the closest star we know of, is still roughly 9,000 times farther from us than Voyager 1 has traveled in the nearly 5 decades since we launched it. The fastest object humanity has ever launched is the Parker Solar Probe, and if you tell people it can travel from Los Angeles to New York in roughly 20 seconds, most of them are impressed. They should be. 450,000 miles per hour is a number that belongs to a different category of speed than anything else humans have ever put into motion. A commercial airliner takes around 5 hours to cross the continental United States. A rifle bullet would take several hours. The Parker Solar Probe does it before you finish reading this sentence. By any measure that human experience can offer, this spacecraft is moving at something close to incomprehensible velocity. And then you ask how long it would take to reach Alpha Centauri, and the answer arrives like a door closing. At that peak speed, 450,000 miles per hour, the fastest any human-made object has ever traveled, The Parker Solar Probe would need approximately 6,600 years to cover the distance to our nearest stellar neighbor. Not centuries, not a few thousand years in a rough sense, 6,600 years. The Roman Empire had not yet risen when that journey would have needed to begin. That is what interstellar distance does to the fastest thing we have ever built. It helps to understand where that speed comes from. The Parker Solar Probe does not maintain 450,000 miles per hour at all times. That figure is a peak, reached at the moment of closest approach to the Sun, when the spacecraft dives inside the orbit of Mercury and uses the Sun's own gravity to slingshot itself to extraordinary velocity. It is a remarkable trick of orbital mechanics. But the craft is not cruising at that speed across interstellar space. It is accelerating and decelerating in a loop around the Sun, a very different thing from driving straight outward toward another star at sustained maximum speed. The number is real, but what it means in the context of reaching another star system requires the full weight of the distance problem that came before it. Then there is Voyager 1. Launched in 1977, it is the most distant human-made object in existence. For nearly 5 decades, it has been pushing outward, past the planets, through the outer reaches of the solar system, and finally into the interstellar medium beyond the heliopause. Voyager is genuinely out there, in the space between stars. It crossed into interstellar space in 2012, 35 years after launch. This is one of the genuine achievements of the space age, and it deserves the awe it receives. Voyager 1 is currently traveling at roughly 38,000 miles per hour, about 17 kilometers per second. That is less than 0.006% of the speed of light. At that rate, covering the 25 trillion miles to just past the halfway point to Alpha Centauri would take something in the neighborhood of 70,000 years. The spacecraft that has been flying longer than most countries have existed in their current form has barely moved by interstellar standards. What astronomers find striking is not that these spacecraft are slow. What is striking is how fast they actually are, and how completely that speed fails to matter. The engineers who built Voyager and Parker were not working carelessly. These machines represent the highest performance ever achieved in the history of propulsion. And yet the gap between what we can do and what interstellar travel requires is so vast that the difference between our slowest interstellar-capable probe and our fastest spacecraft is almost irrelevant. Whether it takes 70,000 years or 6,600 years to reach Alpha Centauri, the answer is the same. Nobody is going there. Here is what causes this. Chemical rockets work by burning propellant and expelling the exhaust at high velocity out the back. The faster the exhaust moves, the more thrust you get. The most advanced chemical propellants humans have developed, liquid hydrogen and liquid oxygen, burn together in the kind of engines that launch the Apollo missions and today power rockets like the Falcon 9 upper stage, produce exhaust velocities of around 4.5 kilometers per second. That is a physical ceiling imposed by chemistry. There is no combination of chemical compounds that releases enough energy to push exhaust significantly faster than this. You cannot engineer around it. You cannot fund your way past it. The limit is in the chemical bonds themselves, in how much energy is stored in the molecules and released when they react. The engineers designing Voyager and Parker knew this. Every trajectory decision, every gravity assist, every careful burn was an attempt to extract the maximum possible performance from engines that are fundamentally constrained by the physics of combustion. Gravity assists from Jupiter, Saturn, and the Sun itself are used because they are essentially free velocity. The spacecraft borrows momentum from a massive planet or star without burning additional fuel. Without those assists, these probes would be moving considerably slower. Even with them, the result is a few tens of thousands of miles per hour, a small fraction of a percent of the speed of light. The gap between chemical propulsion and interstellar travel is not a gap that engineering patience will close. It is not a gap that more funding closes, or that more ambitious mission planning closes. The energy available from burning even the best chemical propellants is separated from what interstellar travel requires by orders of magnitude. This is what makes the subject so difficult to sit with, because the intuitive response when confronted with a problem is to ask what it would take to scale up. A bigger rocket, more fuel, a longer runway. But the scaling relationship does not cooperate. The problem is not that we need a bigger version of the rocket engines we already have. It is that the entire approach, burning chemical propellant to push a spacecraft forward, runs directly into a mathematical wall that gets worse the faster you try to go. There is an equation at the center of rocket science that most people have never heard of, and it is the single most important reason why interstellar travel is so much harder than building a bigger rocket. It is called the Tsiolkovsky rocket equation, named after the Russian mathematician Konstantin Tsiolkovsky, who worked it out in 1903. The equation describes a relationship that feels simple on the surface and becomes catastrophic the moment you push it toward interstellar speeds. The core of it is this: to make a rocket go faster, you need to expel more mass behind it. To expel more mass, you have to carry more fuel. But that fuel has mass of its own, which means you need additional fuel just to accelerate the fuel you're already carrying. And that additional fuel has mass, and so on. The relationship is not linear, it is exponential. Every time you want to double your final velocity, you do not double your fuel requirement. You square it, then you square it again. The numbers spiral outward into territory that no engineering program on Earth can reach. Tsiolkovsky arrived at his equation long before rockets left the ground, working through pure mathematics in his study in rural Russia. He had limited access to advanced scientific instruments or experimental facilities, yet his theoretical work proved to be foundational to everything that came after. The equation itself is deceptively elegant. Delta V equals the specific impulse times the natural logarithm of the initial mass divided by the final mass. That simplicity masks a brutal truth about the physics of motion in space. Once you understand what the equation is really saying, you cannot unsee it. It haunts every conversation about space exploration that extends beyond our planetary neighborhood. The equation reveals why rocket scientists obsess over every kilogram of payload weight. A single additional kilogram in your spacecraft requires exponentially more fuel to accelerate it to a target velocity. This is why space agencies employ teams of engineers whose sole job is to make things lighter. They strip away insulation. They use exotic materials. They redesign structures to use the minimum amount of material necessary to maintain integrity. And even with all these efforts, the mass ratios required for ambitious missions strain the limits of what is physically possible to construct. A rocket that can reach orbit must be 90% fuel by mass. A rocket that can reach the moon must be even more fuel heavy. the percentage only grows worse as your destination grows more distant. Consider what the equation demands for different scenarios. To achieve a velocity of 10 kilometers per second starting from a standstill, you need a mass ratio of approximately 7 to 1. That means a spacecraft that weighs 1 ton when empty requires 7 tons of fuel. But to achieve 20 kilometers per second, you need a mass ratio of 50 to 1. To achieve 30 kilometers per second, the ratio climbs to 400 to 1. These are not marginal increases. They are catastrophic scaling problems that grow worse with each increment of additional velocity. Engineers call this the tyranny of the rocket equation, and it is not hyperbole. This exponential relationship is why orbital mechanics became such a sophisticated discipline. Rocket scientists learned to use gravity assists and orbital transfers to swing around planets and steal a little velocity from their orbital motion. These techniques allow missions to achieve ambitious goals without requiring the impossible fuel ratios that the rocket equation seems to demand. But all of these tricks work because we are still operating within the solar system, where destinations are relatively close and where we can take months or years to reach them. Interstellar distances demand something fundamentally different. This is worth committing to memory. The best chemical rocket engines humanity has ever built, the kind that launched astronauts to the moon, the kind that pushed the Voyager probes out of the solar system, achieve exhaust velocities of roughly 4 kilometers per second. That is the speed at which burned propellant exits the nozzle. It sounds fast. It is, in any ordinary context, extraordinarily fast. But 4 kilometers per second is approximately 0.0013% of the speed of light. The gap between that number and the speeds required for interstellar travel is not a gap you close with better manufacturing or improved nozzle geometry. It is a chasm that swallows the entire concept. To reach the nearest star in a time frame that a living human crew could actually survive, decades rather than millennia, you need to travel at somewhere between 5% and 20% of the speed of light. That range deserves to sit for a moment, because it sounds like a narrow technical specification, and it is actually an enormous problem. 5% of the speed of light is roughly 33 million miles per hour. 20% is approximately 134 million miles per hour. These are not speeds that exist anywhere in human engineering. They are not speeds that exist anywhere in human experience. The fastest thing our civilization has ever built, the Parker Solar Probe at its closest solar pass, reaches around 450,000 miles per hour. That is 0.15% of the speed of light. To get to 5% of light speed from where we are now requires a 33-fold improvement over the fastest object humanity has ever constructed. To reach 10% requires something closer to 65 times better. These are not the kinds of improvements that come from building a bigger version of what we already have. They are not the product of better materials or more funding or another decade of incremental engineering. They represent a category leap. Here is something worth sitting with. At 10% of light speed, the trip to Proxima Centauri takes roughly 42 years. That is long, but a crew could plausibly survive it. Crew members who are 30 years old at departure arrive in their early 70s. At 20% of light speed, the journey takes around 21 years. That is within a single working career. These numbers explain exactly why the 5 to 20% range is the target. Below 5%, You are looking at a journey lasting longer than a human lifespan, even for the youngest possible crew. Above 20%, you begin encountering a different set of physics problems that compound in ways that make the energy requirements even more brutal. The window is real. The engineering required to hit it is something we cannot currently do and have no clear path to doing. To put those speeds in the most concrete terms possible, at 10% of light speed, a spacecraft crosses the distance between Earth and the Moon in less than 1.5 seconds. The entire diameter of the solar system, out to Neptune, takes roughly 5 hours. These numbers feel fast because they are genuinely fast. They are also still only a fraction of what light manages effortlessly. Light crosses the solar system in about 4 hours. The gap between what light can do and what we are trying to do is still enormous, even at the upper end of our target range. What happens when you start pushing past 20% or 30% is where the physics gets strange in a new way. Einstein's special relativity predicts that as a massive object accelerates toward the speed of light, it doesn't just get faster, its effective inertia increases. The object resists acceleration more strongly the faster it is already moving, and it does so in a way that is not linear but exponential. At 10% of light speed, the relativistic correction is small enough that Newtonian mechanics gives you a roughly accurate picture. At 50%, the corrections become significant. At 90%, the energy required to push the spacecraft to 91% is vastly greater than the energy required to get it from 89% to 90%. The curve steepens toward a vertical line at the speed of light itself. Time dilation enters the picture here too. A crew traveling at 90% of light speed would age more slowly than people on Earth. Their clocks, their metabolism, their experience of time would all run at a slower rate relative to a stationary observer. This sounds, at first, like an advantage. The crew could make a journey that takes 50 years of Earth time while only aging perhaps 20 years aboard the spacecraft. The problem is not the physics of time dilation. The problem is what it costs to reach the speeds at which time dilation becomes meaningful. Getting a spacecraft to 90% of light speed requires energy inputs that dwarf everything we have discussed so far. The relativistic energy equation does not offer a shortcut. It offers a punishment. The faster you go, the more the universe charges you for each additional increment of speed. At 10% of light speed, the kinetic energy of a modest spacecraft already exceeds the annual energy output of every power plant on Earth combined. At 50%, you multiply that by something closer to a factor of 15. At 90%, you are in territory where the numbers become almost meaningless to write out, because nothing in the physical infrastructure of human civilization approaches the capacity to generate them. The universe is not indifferent to mass moving at high velocity. It actively resists it, and the resistance grows without limit. This is why the 5 to 20% window matters so much, and why even hitting the bottom of that range represents the central unsolved problem of interstellar propulsion. It is fast enough to make a crewed mission conceivable. It is not so fast that the relativistic energy curve makes the calculation obviously hopeless. But it is still speeds that require energy delivery systems nothing on Earth currently resembles. The closer you get to light speed, the more energy each additional increment of velocity costs, and at some point, the energy required passes from merely staggering to physically impossible. which is the wall that every serious interstellar propulsion concept is ultimately trying to get around. Of all the propulsion concepts that have ever been seriously analyzed with real engineering and real math, nuclear options come closest to bridging the gap between where we are and where we would need to be. The first branch is called nuclear thermal propulsion, and it works roughly the way it sounds. Instead of burning chemical fuel to heat a gas and push it out of a nozzle, you run a nuclear reactor, use the heat from fission to raise a propellant like liquid hydrogen to extreme temperatures, and then expel it. The hotter the propellant gets, the faster it exits the nozzle, and the faster the exhaust exits, the more thrust you generate per kilogram of fuel carried. This matters enormously because exhaust velocity is the number that determines how efficient a rocket is. Chemical rockets hit a ceiling here. The chemical energy stored in the best propellant combinations simply cannot heat gases beyond a certain temperature. Nuclear reactors have no such ceiling in the same way. This is not a theoretical concept waiting to be proven out. Engineers actually built and tested nuclear thermal engines. The NERVA program in the United States ran throughout the 1960s and into the early 1970s, producing engines that achieved roughly twice the efficiency of the best chemical rockets of the era. The tests were real. The thrust was real. The technology worked. At one point, there were serious plans to use NERVA engines for a crewed Mars mission in the 1970s. Then funding dried up, priorities shifted, and the program ended without ever flying a mission. The hardware sat in Nevada and was eventually decommissioned. Here is the problem though. Twice as efficient as a chemical rocket is meaningful for missions within our solar system. It is nowhere near enough for anything interstellar. Even a rocket twice as efficient as our current best would still require tens of thousands of years to cross the distance to Alpha Centauri. Doubling performance when you need to multiply it by a factor of 1,000 or more does not move the needle in any practical sense. Nuclear thermal gets you further, faster, with less fuel than chemical propulsion. It does not get you to the stars. What might is a different nuclear idea entirely, and it is one of the stranger engineering proposals in the history of spaceflight. Project Orion was conceived in the late 1950s by a group of physicists that included Freeman Dyson. The concept was blunt in a way that is almost difficult to take seriously at first. You detonate nuclear bombs behind the spacecraft in rapid sequence. A massive pusher plate at the rear absorbs the shock of each blast through a system of shock absorbers, and the spacecraft accelerates with every detonation. Not a gentle push. A series of nuclear explosions, each one slamming the ship forward. Dyson ran the numbers seriously. What he found was that an Orion-type vehicle could achieve exhaust velocities roughly 10 times better than nuclear thermal engines. Dramatically better. His estimates suggested that a full-scale Orion spacecraft could reach somewhere around 0.1% of the speed of light, and in a more optimistic configuration, potentially higher. The math indicated a travel time to Alpha Centauri of somewhere in the range of 1,300 years. That sounds discouraging, and in terms of a crewed human mission, it absolutely is. But compare it to the tens of thousands of years required by anything chemical, and you begin to understand why physicists took it seriously. Orion was a genuine leap in a direction that nothing else at the time could match. The concept was never built. The Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, effectively ended Orion as a practical program. The political and environmental objections were real, and the vision faded. But the physics behind it never went away, and it fed directly into what came next. In the 1970s, the British Interplanetary Society spent 5 years on a project called Daedalus, which was perhaps the most ambitious and rigorous interstellar spacecraft design study ever completed. The goal was specific: design an unmanned probe that could reach Barnard's star, roughly 6 light-years away, within 50 years of departure. Not a rough sketch, an actual engineering design with calculations, component specifications, and honest accounting of what was required. The engine concept they arrived at was nuclear pulse propulsion of a different kind than Orion. Rather than full-scale nuclear bombs, Daedalus would ignite tiny pellets of deuterium and helium-3 fuel using electron beams, triggering small fusion reactions 250 times every second. The exhaust from those rapid micro-explosions would drive the spacecraft forward. The design called for a 2-stage vehicle with a total mass at departure of around 54,000 tons, the overwhelming majority of which was fuel. The second stage alone, the part that would continue after the first stage was jettisoned, carried a payload of roughly 450 tons of scientific instruments. The projected performance was remarkable. The design team calculated that Daedalus could accelerate to approximately 12% of the speed of light. At that velocity, Barnard's star was reachable in about 50 years. That is a genuine interstellar mission, not a multi-thousand-year crawl, not a generational voyage, a designed, engineered journey that a civilization could launch and receive results from within a human lifetime. Then the problems arrive. Helium-3 is extraordinarily rare on Earth. The quantities Daedalus required do not exist here in any accessible form. The design team proposed mining it from the atmosphere of Jupiter, which was, even by the standards of the 1970s, an operation that would require decades of industrial-scale extraction using technology that did not exist. The fusion ignition system was speculative in ways its designers acknowledged openly. The spacecraft had no braking system whatsoever. It would arrive at Barnard's star at 12% of light speed and fly straight through the system in a matter of hours, transmitting data as quickly as it could before the target was already behind it. These were not small problems. They were enormous ones. But what Daedalus demonstrated was something important. With nuclear pulse fusion propulsion, the numbers for genuine interstellar travel are not obviously impossible in the way they are for chemical rockets. The physics allows it. The engineering is extraordinarily hard and requires capabilities far beyond what we currently possess. But the concept does not break any fundamental laws. It just requires things we haven't built. Daedalus remains the most thoroughly engineered interstellar spacecraft design ever attempted, and the fact that it was designed 50 years ago and we still cannot build it tells you something important about where the real barriers lie. Fusion propulsion is the version of nuclear power that would actually change the equation for interstellar travel. The reason it hasn't changed anything yet is that we haven't figured out how to do fusion. To understand why fusion is different from the fission systems covered in Project Daedalus and Project Orion, you have to understand what fusion actually does at the atomic level. Fission splits heavy atoms apart, uranium, plutonium, and releases energy from that splitting. Fusion does the opposite. It forces light atoms together. Hydrogen isotopes like deuterium and helium-3 fuse into heavier elements. In that collision, they release far more energy per unit of mass than any fission reaction can produce. The numbers are not close. A kilogram of deuterium-helium-3 fuel, fully fused, releases roughly 10 times the energy of an equivalent mass of fission fuel. Hundreds of thousands of times more energy than the best chemical propellants we have ever burned. This is the energy density that interstellar travel needs. This is what makes the math start to look different. The exhaust products of a fusion reaction move extremely fast. If you can channel those products out of a nozzle in a controlled direction, the resulting thrust carries a specific impulse, a measure of engine efficiency that dwarfs anything fission or chemistry can produce. A well-designed fusion rocket using deuterium and helium-3 could theoretically achieve specific impulses hundreds of times greater than the most advanced chemical engines ever built. At those performance levels, the rocket equation stops being quite so murderous. A spacecraft could accelerate to 10 or 15% of the speed of light, carrying a fuel load that is at least physically conceivable. Proxima Centauri in 30 or 40 years becomes a number you can write down without immediately discarding it. That is not a small thing. That is the difference between a mission that fits inside a human lifetime and one that requires a civilization to outlast the crew. The problem is that we cannot do this, not even close. Controlled nuclear fusion, the kind where you force atoms together and extract more energy than you put in, has been the central goal of plasma physics for more than 6 decades. The basic physics has been understood since the 1950s. The challenge is containment. Fusion requires temperatures of tens of millions of degrees, hotter than the core of the sun. No material in existence can hold plasma at those temperatures directly. That means researchers have spent decades building magnetic confinement systems, tokamaks, stellarators, or using powerful lasers to compress fuel pellets so rapidly that fusion occurs before the plasma can escape. The National Ignition Facility in California achieved a historic milestone in late 2022, producing more energy from a fusion reaction than the lasers used to trigger it. This was genuinely significant. It was also a single controlled pulse in a building the size of a sports stadium, producing a fraction of a second of net energy gain under conditions that have no relationship to a compact spacecraft engine. The gap between that result and a fusion drive capable of pushing a spacecraft to 15% of light speed is not a gap of engineering refinement. It is a gap of fundamental capability. Building a fusion reactor that runs continuously, fits aboard a spacecraft, survives decades of operation, channels its output efficiently into directed thrust is not the next step after NIF. It is many steps beyond anything we currently know how to build. Every serious proposal for fusion propulsion assumes technologies that researchers are still working to make viable on the ground, let alone in space. Then there is the Bussard ramjet. Robert Bussard proposed it in 1960. The concept has a certain elegance that makes it hard to forget. Instead of carrying fusion fuel, the spacecraft deploys a vast electromagnetic funnel, hundreds or thousands of kilometers across, that scoops interstellar hydrogen as it travels and feeds it continuously into a fusion reactor. The fuel is everywhere. The ship never runs out. In principle, such a vessel could accelerate indefinitely, approaching light speed over a long enough journey with no limit imposed by the fuel it carries at departure. The problems, when you look closely, are severe. Interstellar hydrogen is genuinely sparse, about 1 atom per cubic centimeter in the regions between stars. Collecting enough of it to sustain fusion requires scooping an enormous volume per second at high speed. The electromagnetic field needed to do that produces drag. Calculations suggest the drag from sweeping that field through the interstellar medium may exceed the thrust produced by the reactor, meaning the ramjet could actually slow down rather than accelerate. The proton-proton fusion cycle that would process ordinary interstellar hydrogen is also far harder to initiate and sustain than deuterium fusion. It requires conditions even more extreme than the reactions being pursued in current fusion research. The RAM scoop remains a beautiful idea that has not survived contact with detailed physics. What fusion propulsion represents, at this moment in history, is a ceiling we can see clearly and cannot reach. The physics is not in doubt. The energy is real. The exhaust velocities are real. The mission profiles are calculable. None of that matters until the engineering catches up. The engineering has not caught up with even the first requirement, a fusion reaction that runs reliably and produces net power at a useful scale. Until we achieve reliable, controllable, compact fusion, a goal the physics community has been pursuing since before most people alive today were born, fusion rockets remain a propulsion concept that exists entirely on paper. The most elegant solution to the fuel problem is to not carry fuel at all, and the physics of light pressure gives you a theoretically valid way to do exactly that. Every propulsion concept covered so far shares the same fundamental burden. You carry your energy source with you. Whether it is chemical propellant, a nuclear reactor, or pellets of deuterium fuel, the spacecraft has to haul whatever it is going to burn, and that mass creates the exponential spiral the rocket equation describes. Light sails sidestep that spiral entirely. The energy stays on the ground. The spacecraft carries almost nothing. You push it from behind with photons, and photons weigh nothing at all. This is not a theoretical abstraction. Light exerts real pressure. It has been measured in laboratories. Every photon that strikes a surface transfers a tiny but real amount of momentum to whatever it hits. The effect is small. Sunlight pushing on your palm delivers a force about 1 trillion times too weak to feel. But in the vacuum of space, with no friction and no air resistance, even a tiny continuous force accumulates. Solar sails have already been demonstrated in actual flight. Japan's Ikaros spacecraft, launched in 2010, used a 14-meter reflective sail to accelerate measurably under sunlight alone. The concept is not speculative. The physics is settled. What is not settled is whether you can scale the force up to something useful for interstellar distances. The sun's light is not enough. Even a perfectly reflective sail the size of a city block, pushed by sunlight at Earth's distance from the sun, would take hundreds of thousands of years to reach Proxima Centauri. The pressure is real but faint. To get the force you actually need, you have to replace sunlight with something far more intense. That is where the laser comes in. Philip Lubin at UC Santa Barbara has spent years working out what a laser-driven sail would actually require. The proposal is straightforward in principle. Build a large array of lasers on the ground or in orbit and aim them at a reflective sail attached to a small spacecraft. Lasers concentrate their energy in a way that sunlight cannot. A sufficiently powerful laser array could, in theory, push a sail to a significant fraction of the speed of light. The math works. The physics permits it. There is no law of nature being violated. The numbers, however, are staggering. To accelerate even a modest payload to around 20% of the speed of light, the laser array would need to produce somewhere in the range of 100 gigawatts of focused power. That figure is roughly 10 times the combined output of every nuclear power plant currently operating on Earth, all channeled into a single coherent beam, held steady for several minutes. Nothing remotely close to this infrastructure exists. Building it would represent an engineering undertaking larger than any in human history. Then there is the beam divergence problem. Lasers spread as they travel. Even the most tightly focused beam in the world gradually widens with distance. A laser array the size of a kilometer, aimed at a sail that has traveled a few million kilometers away, is already losing coherence. By the time the sail has reached a fraction of a light year, the beam has spread so thin that it is delivering almost nothing. The window during which the laser can actually push the sail is surprisingly short. You get minutes of effective acceleration, and then the sail is on its own, coasting at whatever speed it reached before the beam gave out. This limits how much velocity you can impart, regardless of how powerful the array is, because the sail moves away from the beam faster than the beam can stay useful. The sail itself presents problems that have no obvious solution. To accelerate a sail to 20% of light speed in a few minutes, the photon pressure has to be enormous, which means the heating rate on the sail material is extreme. The sail has to be nearly perfectly reflective, absorbing even a fraction of a percent of the incoming laser energy would heat it catastrophically in seconds. Materials with the required reflectivity, thinness, and heat tolerance do not currently exist, though researchers are exploring candidates like molybdenum disulfide and similar engineered films. This is an engineering problem, not a physics problem, which means it might eventually be solvable, but it has not been solved. Here is the part that stops the whole concept for any crewed mission. A laser sail has no brakes. Once the laser array is behind you and out of range, you are traveling at 20% of the speed of light with no mechanism to slow down. The only way to decelerate at the destination would be another laser array waiting for you at Proxima Centauri, pointed back in your direction, powerful enough to stop you. You cannot build that array before you leave. You cannot send it ahead because it would have the same stopping problem. There is no solution to this that doesn't require infrastructure at the destination that you have no way to place there. For a robotic probe, this is a serious inconvenience. The probe flies through the Alpha Centauri system at a fifth of the speed of light, takes measurements during a brief window, and transmits what it can before the system disappears behind it. That is scientifically useful. It is not nothing. Arriving at Proxima Centauri at 20% of the speed of light, with no way to slow down, is not interstellar travel. It is an interstellar flyby lasting a matter of hours, and for a crewed mission, it is a death sentence. In 2016, a group of scientists and investors announced the most serious and well-funded interstellar mission concept in history, and what they proposed was to make the spacecraft smaller, not faster. The reasoning was direct. Every previous interstellar concept had collapsed under the weight of its own ambitions. Fusion engines, nuclear pulse drives, massive crewed vessels, they all required either technology that didn't exist or energy budgets that no realistic power source could meet. Breakthrough Starshot, backed by Russian billionaire Yuri Milner with an initial $100 million, and supported by figures including Stephen Hawking and physicist Philip Lubin, approached the problem differently. If the physics of a laser sail fundamentally works, but the laser required to push a meaningful payload is too large to build, then the answer is to shrink the payload until the laser becomes buildable. Not a crude spacecraft, not a probe the size of a refrigerator. A complete spacecraft etched onto a wafer roughly the size of a postage stamp, weighing about a gram, attached to a sail perhaps a few meters across. They called it a starship. The concept rests on real physics. A gram-scale spacecraft, pushed by a laser array producing around 100 gigawatts of focused power, could be accelerated to roughly 20% of the speed of light within minutes. At that velocity, the journey to Alpha Centauri takes approximately 20 years. That is a number a living person can hold in their head. Someone born today could be in their 20s when the probe arrives. The mission suddenly exists within a human time frame rather than requiring civilizational patience. This number deserves your focus. 20% of light speed is about 134 million miles per hour. The fastest spacecraft humanity has ever built peaks at roughly 450,000 miles per hour. Starshot is proposing something 300 times faster than our current record, and the path to achieving it runs not through exotic new physics, but through scaling up a laser array and scaling down a spacecraft. The engineering is brutal, but the physics is not in question. The laser array itself is the first enormous obstacle. 100 gigawatts is not a number that fits easily into any current infrastructure. That is roughly 10 times the combined output of every nuclear power plant in the United States, focused into a single coherent beam and sustained for several minutes during each launch. The array would need to be built somewhere with stable atmosphere and extreme precision, probably at high altitude. Individual lasers would have to be synchronized with a precision that pushes against the limits of current optical engineering. All of it is far beyond anything built so far. Then there is the dust. This problem sits at the center of everything and does not go away. The interstellar medium is not empty. It contains hydrogen atoms, helium atoms, and scattered grains of dust at densities that sound almost negligible, roughly 1 grain per cubic centimeter across enormous volumes. At low speeds, none of this matters. At 20% of light speed, a particle the size of a bacterium strikes with the energy of a rifle bullet. A grain of dust the size of a sand particle carries the destructive force of a small explosive. The sail, already a thin reflective sheet measured in grams, would be perforated and shredded within hours of reaching full speed, unless some solution is developed. Proposals include coating the sail with materials that ablate cleanly under impact, rather than tearing, shaping the sail geometry to deflect incoming particles, or designing the chip to be robust against the loss of portions of its sail. None of these approaches have been tested at anything resembling the required conditions because we have never moved anything at those speeds. The communication problem is equally severe. A gram-scale probe broadcasting from 4.24 light-years away with a transmitter drawing milliwatts of power produces a signal that arrives at Earth approximately 1 billion times fainter than the already faint signals received from the Voyager spacecraft. Receiving it would require a radio telescope array covering something on the order of a city block, coordinating its receivers with extraordinary precision. The signal delay alone is 4.24 years each way. so there is no possibility of any interactive guidance. Whatever the chip observes at Alpha Centauri, Earth learns about more than 4 years after the flyby occurred. And it is a flyby. There is no braking mechanism. A starship arriving at Alpha Centauri at 20% of light speed passes through the system in a matter of hours. Whatever cameras and sensors it carries have a brief window to gather data before the system is behind it forever. The probe cannot orbit. It cannot slow down and look more carefully. It collects what it can during a few hours of close approach and then spends the next 4 years sending that data home. These are not minor details waiting to be worked out by the engineering teams. They are fundamental challenges at the core of the design, each one requiring a solution that does not yet exist. The Starshot team has been open about this. The $100 million is not a construction budget. It is a research budget, aimed at determining whether the unsolved problems are solvable in principle before committing to larger expenditures. What Starshot has done, more than any previous concept, is move the conversation from theoretical speculation to specific engineering problems with specific targets. That is genuine progress, even if the destination is still very far away. Starshot is the most honest attempt anyone has made to build something that could actually reach another star. And the list of problems that still need solving is long enough that nobody involved claims we know how to build it yet. There is a second wall beyond the rocket equation, and this one is not about propulsion design or fuel efficiency. It is built into the geometry of space and time itself. Every propulsion concept covered so far, nuclear pulse, fusion rockets, laser sails, the gram-scale wafers of breakthrough Starshot, runs into the same deeper problem eventually. You can solve the fuel question. You can solve the exhaust velocity question. You can, in theory, build an engine that makes every previous engine look primitive. And then you open a physics textbook from 1905 and discover that Albert Einstein already described a barrier your engine cannot cross, no matter how well it is built. That barrier is not a gap in our understanding. It is a feature of how the universe is structured, and it has been sitting in the equations for over a century. Here is the core of it. When Einstein published his special theory of relativity, one of the consequences, buried in the mathematics, not immediately obvious, was that mass and energy are not separate things. They are different expressions of the same thing. The famous equation, E equals mc squared, is the relationship between them. What this means for a moving spacecraft is not immediately dramatic. At ordinary speeds, the relativistic effects are so small, they are essentially invisible. A spacecraft moving at 1% of light speed, fast enough to cross the continental United States in a fraction of a second, behaves almost exactly the way Newton's equations would predict. The corrections from relativity are tiny, manageable, ignorable. Then you push harder, and the universe pushes back. As a spacecraft accelerates toward a significant fraction of light speed, something strange begins happening to its effective inertia. It resists acceleration more and more, not because anything mechanical is changing, but because the structure of spacetime itself is resisting. The object accumulates what physicists sometimes describe as relativistic mass. The faster it goes, the harder it becomes to push it faster. At 10% of light speed, the relativistic correction is modest, roughly 0.5% above what Newton would predict. You would need slightly more energy than classical mechanics suggests, but not dramatically more. At 50% of light speed, the correction becomes significant. You need roughly 15% more energy than Newtonian physics would imply. At any 90% of light speed, you need more than twice the Newtonian prediction. At 99%, the energy required is about 7 times what a pre-relativistic calculation would give you. And as you approach 100%, as you close that final gap toward the speed of light itself, the energy requirement does not plateau, does not level off, does not reach some very large but finite number. It goes to infinity. Literally, mathematically, physically, infinite energy would be required to push a massive object to the speed of light. Not a great deal of energy. Not more energy than any civilization could reasonably generate. Infinite energy. This is not a technology problem. It cannot be solved by building a better reactor or discovering a more energetic fuel. The speed of light is not a speed limit in the way that a highway sign is a speed limit, something that authorities post and that sufficiently motivated drivers occasionally ignore. It is woven into the structure of space-time. Nothing with mass gets through it. The universe simply does not allow it. What this means in concrete terms is worth sitting with. Accelerating a spacecraft of 1,000 tons, not an enormous vessel, smaller than many naval ships, a modest crewed craft, to 10% of light speed requires energy roughly equivalent to everything humanity has extracted and burned from all the oil deposits ever found on Earth. Every barrel, every refinery, every combustion engine running continuously throughout all of recorded industrial history. That gets you to 10%. To push the same spacecraft to 50% of light speed, you would need something in the range of 100 times that energy. To reach 90%, thousands of times more. The numbers stop feeling like numbers at a certain point. They become abstract in the way that geological time is at best. Racked, acknowledged intellectually, impossible to feel. Interstellar space is not a perfect vacuum. The interstellar medium contains gas atoms and dust grains at extraordinarily low density, but density is not zero. A spacecraft moving at a substantial fraction of light speed does not coast freely through this environment. It collides with particles continuously, and at high speeds those collisions are not gentle. They transfer energy. They slow the spacecraft. They generate radiation. Maintaining speed against this interstellar drag requires ongoing energy expenditure, which means the energy budget for an interstellar mission is not just the cost of acceleration. It includes the cost of fighting the medium for years or decades of transit. The faster you go, the more energetic each collision, and the greater the drag you must overcome to hold your velocity. Some researchers have pointed out that the relativistic energy wall looks different depending on what you are accelerating. A 1-gram Starshot wafer requires far less energy to push to 20% of light speed than a crewed vessel of any realistic mass. But the wall does not disappear for small objects. It just shifts. The laser array required to push even a gram-scale probe to relativistic speed represents an energy delivery system of extraordinary scale, and scaling up from a gram to anything capable of sustaining human life reintroduces the energy problem in full force. The relativistic energy wall is not the same as the rocket equation. The rocket equation is a problem about how you carry fuel. In principle, if you found a propellant with extraordinary energy density, you could ease the rocket equation's constraints substantially. The relativistic energy wall is different. It does not care how you generate the energy or where it comes from. It cares only that you are accelerating mass, and it charges more for each increment of speed as you get faster, in a way that no engineering cleverness can reduce. The only proposals that avoid the relativistic energy wall are the ones that don't accelerate mass in the conventional sense at all, and those proposals come with a different set of problems that are, if anything, harder. In 1994, a physicist named Miguel Alcubierre published a paper that caused a quiet sensation in the theoretical physics community because he had apparently found a loophole in general relativity that allowed for faster-than-light travel without violating any known laws. The paper was not long. It did not claim to have solved engineering problems or propose a construction schedule. What it did was something more fundamental and, in some ways, more unsettling. Alcubierre took Einstein's field equations, the same equations that describe black holes, gravitational waves, and the expansion of the universe, and found a solution hiding inside them, a solution that nobody had noticed before. The solution described a region of space-time that could move through the universe faster than light, carrying whatever was inside it along for the ride. The spacecraft itself would not be moving faster than light relative to its immediate surroundings. It would be sitting still inside a bubble while the bubble moved. Space in front of the bubble would contract. Space behind it would expand. The net effect, viewed from outside, would be a vessel crossing interstellar distances in years rather than millennia, with no violation of special relativity, no infinite energy demand from the relativistic mass equation, and no time dilation experienced by the crew. This is not hand-waving. The mathematics is published, peer-reviewed, and accepted as a valid solution within general relativity. Physicists did not dismiss it. They took it seriously, and then they started looking for the catch. The first catch is substantial enough to stop most conversations cold. The Alcubierre geometry requires a region of negative energy density surrounding the spacecraft. Not low energy, not zero energy. Negative energy, a condition in which the energy content of a region of space is less than the energy of a perfect vacuum. This is exotic matter in the most literal sense of the phrase. Nothing in our catalogue of known particles or fields behaves this way at any useful scale. There is a quantum mechanical phenomenon called the Casimir effect, in which two uncharged metal plates placed very close together experience a tiny attractive force because quantum fluctuations between them are suppressed relative to the fluctuations outside. This produces something resembling a negative energy density in the narrow gap between the plates. It is real, it has been measured, and it is roughly as useful for building an Alcubierre drive as a birthday candle is for powering a city. The scale of negative energy required for an Alcubierre bubble large enough to contain a spacecraft was calculated by Alcubierre himself and later by others in more detail. The numbers that came back were staggering. To warp spacetime around even a small vessel, the required exotic matter carries a mass-energy equivalent roughly comparable to the planet Jupiter. In negative form, the universe does not appear to contain anything like that, and we have no theoretical basis for believing it could be manufactured. The second catch is stranger. A spacecraft inside an Alcubierre bubble is causally disconnected from the walls of the bubble around it. Information cannot travel faster than light, even inside the bubble. This means the crew cannot send signals to the outer edge of the bubble to steer it, modify it, or shut it down. Whatever instructions were programmed into the bubble geometry before departure are locked in. The crew becomes passengers in the most extreme possible sense, unable to alter their trajectory, unable to respond to anything they discover in front of them, unable to stop. For a crewed mission to another star system, this is not a navigational inconvenience. It is a fundamental operational impossibility. The third catch was identified later and is perhaps the most darkly ironic. As the bubble moves through space, high-energy particles from the interstellar medium pile up on its leading edge, blue shifted by the contraction of space-time ahead of the vessel. They accumulate during the journey. When the bubble decelerates or collapses at the destination, all of that stored energy releases in a burst pointed directly at whatever the spacecraft was traveling toward. The act of arriving would likely irradiate and destroy the destination. This is, to put it gently, a significant design flaw. Then came Harold White. In 2012, a physicist working at NASA's Johnson Space Center proposed a modification to Alcubierre's original geometry. White argued that changing the shape of the warp bubble from a simple shell into a torus, a donut shape oscillating at the right frequency, could reduce the exotic matter requirement dramatically. His calculations suggested the energy needed might drop not just by orders of magnitude, but to something resembling the mass energy of a small automobile. This was a remarkable claim, and it attracted significant attention, including funding for a small experimental program at NASA. For a few years, the possibility felt less remote. Later, analysis found errors in the approach. The oscillating geometry did not produce the savings White had calculated, and when other physicists worked through the numbers more carefully, the exotic matter requirements returned to their original catastrophic scale. The energy of a small car became, again, the energy of a planet, in negative form. White's work was not fraudulent. The field equations are genuinely complicated, and the geometry involved is not intuitive. But the correction was discouraging. The shortcut had closed. What Alcubierre's paper established, and what 3 decades of follow-on work has confirmed, is that general relativity does not obviously forbid faster-than-light travel through space-time manipulation. It merely requires conditions that appear nowhere in the observable universe and may be fundamentally incompatible with quantum field theory. The math that works in general relativity may be vetoed by the deeper physics underneath it. There is a theorem by Hawking and others suggesting that any space-time geometry allowing faster-than-light transit will also produce conditions that quantum effects would likely destroy. The bubble, in other words, might be self-cancelling at a quantum level, regardless of how valid it looks in classical general relativity. The Alcubierre drive is the most honest attempt physics has ever made to find a faster-than-light solution that doesn't break the rules. And the conclusion after 30 years of analysis is that the rules still win. General relativity, the same theory that makes GPS satellites work and predicted black holes before anyone found one, also allows for shortcuts through space-time. And the reason we can't use them tells you a great deal about how deep the problems with interstellar travel really go. In 1935, Albert Einstein and his colleague Nathan Rosen were working through the mathematics of general relativity when they found something unexpected buried in the equations. The geometry of space-time under certain conditions, allowed for what they called bridges, pathways connecting two distant regions of the universe through a tunnel in the fabric of space itself. Not a metaphor, not a rough approximation. A mathematically valid solution sitting inside the same equations that describe how planets orbit and how light bends around massive objects. These structures were later renamed wormholes, and the name stuck because it captures something true about how they work. A shortcut carved through the material of space rather than a path across it. In principle, a wormhole could link two points in the galaxy separated by thousands of light years. Transit time through the tunnel itself could be short. The distance you travel inside the wormhole is not the same as the distance between the two mouths in ordinary space. This is not science fiction reasoning. The math permits it. This next point deserves your close attention. General relativity does not care whether its solutions are useful to human beings. The equations describe what space-time can do, and wormholes are one of the things it can do, at least on paper. What the equations do not guarantee is that any of these structures actually exist in the universe, or that they could be created deliberately, or that anything could survive passing through one. That gap between mathematical permission and physical reality is where every wormhole proposal eventually collapses. The first problem is stability. A wormhole that forms naturally under general relativity collapses almost instantly. Not in minutes, not in seconds. In fractions of a second, far too small for any measurement we currently have to detect. The tunnel pinches shut before light itself could cross from one end to the other. This is not an engineering limitation waiting for a solution. It is what the equations predict will happen to an unmodified wormhole. Nothing passes through, nothing survives. The bridge forms and vanishes before it exists in any useful sense. What astronomers needed was a way to hold the tunnel open. The theoretical answer is exotic matter, a substance with negative energy density, meaning it pushes outward against gravity rather than falling inward with it. Exotic matter threaded through the throat of a wormhole would, in principle, keep the walls from collapsing. This is the same exotic matter that the Alcubierre drive requires, the same substance with no confirmed physical counterpart anywhere in the observable universe. The Casimir effect in quantum mechanics produces something that behaves mathematically like negative energy at very small scales, in vanishingly tiny amounts. The quantity of exotic matter required to hold a traversable wormhole open would need to be enormous by comparison, and whether the Casimir effect scales in any useful direction at all remains an open question that has not been answered favorably. Then something stranger compounds the problem. Even setting aside stability and exotic matter, forming a wormhole in the first place appears to demand energy densities found only in conditions that no human technology can approach. The early universe, fractions of a second after the Big Bang, had those conditions. The region immediately surrounding a black hole approaches them. We cannot recreate either environment. We cannot manufacture the starting conditions that would allow a wormhole to form and then stabilize it before it collapses. The entire sequence, formation, stabilization, traversal, requires physics operating at scales and energies that sit entirely outside anything we have built or currently know how to build. There is also a deeper objection. Stephen Hawking spent years developing what he called the chronology protection conjecture, and the reasoning matters here. Any shortcut through space-time that allows faster than light travel does not just connect two places, it connects two moments in time. A wormhole traversed in the right sequence could, under the mathematics, allow travel into the past. Hawking argued that the laws of physics conspire to prevent this, that quantum effects at the microscopic level would generate feedback that destroys any structure capable of creating a time loop before it could be used. This is not a proven theorem, it remains a conjecture, but the reasoning behind it is taken seriously, and it adds another layer to the problem. Even if you solved stability, even if you found exotic matter, the resulting structure might be self-defeating at a quantum level that we cannot observe directly. There is also the question of aim. Wormholes have two mouths, and both mouths have to be somewhere. Even in theoretical discussions where all other problems are set aside, nobody has proposed a mechanism for positioning one end of a wormhole at a specific star system light years away. You cannot thread a tunnel toward a destination you have no physical access to. The wormhole concept has no navigation framework. It connects points in space-time, but which points are not under anyone's control. The exotic matter required to hold a wormhole open is not just something we haven't made yet. It may be something the universe simply does not contain in usable form, which means the shortcut remains, for now, a mathematician's tool rather than an engineer's option. Of all the ways an interstellar journey could kill the people aboard it, radiation is the most persistent and the hardest to engineer around. This was because it is everywhere. It comes from all directions. The most dangerous kinds pass through almost anything you try to block them with. Every other problem in interstellar travel has at least a theoretical solution sitting somewhere on the drawing board. The energy wall might yield to fusion. The dust problem might yield to shielding. The psychological collapse of a crew might yield to careful selection and mission design. Radiation does not yield to any of those answers. It is a background condition of the universe. Present in deep space the way gravity is present on Earth. Not an obstacle you find in your path, but a property of the environment itself that never turns off. To understand why this is such a serious problem, you have to start with what protects you right now. Earth's magnetic field deflects enormous quantities of charged particles that stream in from the sun and from deeper in the galaxy. The atmosphere absorbs most of what gets through. Standing on the surface, you receive a radiation dose low enough that your body's repair mechanisms handle it without difficulty. Astronauts on the International Space Station receive doses roughly 10 times higher than people on the ground. Even they are still partially shielded by the outer edges of Earth's magnetic field. Move beyond that field entirely, into the deep space environment where any interstellar mission would spend essentially all of its journey, and the shielding disappears. There is nothing between the crew and the full radiation environment of the galaxy. That environment has two main components, and they present very different engineering problems. The first is solar energetic particles, charged particles blasted outward by the sun during flares and coronal mass ejections. These events are dangerous, but they are relatively predictable. A crew with warning time can shelter in a shielded compartment for the hours or days an event lasts. They are a serious hazard, but not an unsolvable one. The second component is the harder problem by a wide margin. Galactic cosmic rays are high-energy particles accelerated by supernova, pulsar winds, other violent events across the galaxy, traveling in every direction through interstellar space. They arrive constantly. They arrive from all sides. and the most energetic ones carry so much momentum that no practical thickness of material stops them entirely. This is the point where shielding runs into physics. Lower energy cosmic rays can be blocked by thick material, lead, polyethylene, water, or some combination. But heavy shielding adds mass, and mass is exactly the thing an interstellar spacecraft cannot afford more of. Every kilogram of shielding material requires more fuel to accelerate. More fuel means more mass. More mass means more fuel still. The rocket equation turns every attempt to protect a crew into a demand for more energy. That then requires more mass, which requires more energy. Beyond a certain thickness, shielding also creates a secondary problem. Incoming particles collide with shielding material and produce secondary radiation in the form of additional particles and gamma rays. Add enough lead, and you have not blocked the irradiation. You have changed it into a different kind of radiation generated right next to the crew. The health effects of long-term exposure to the deep space radiation environment are not theoretical. NASA has studied them carefully, partly because Mars mission planning requires confronting the same problem at a smaller scale. The most immediate concern is cancer. Galactic cosmic rays ionize tissue as they pass through it, damaging DNA in ways that increase the risk of malignant tumors. The increased cancer risk from a multi-year Mars transit, even a round trip lasting 2 or 3 years, pushes against the radiation dose limits that space agencies currently set for their astronauts. Those limits exist because the risk becomes statistically unacceptable beyond certain exposure levels. An interstellar journey lasting decades blows past every established threshold by a factor that is not small. Cancer risk is only part of the picture. NASA-funded research exposed mice to simulated galactic cosmic ray conditions and found measurable cognitive effects, problems with memory, decision-making, spatial reasoning that persisted after exposure ended. The central nervous system turns out to be more vulnerable to heavy ion radiation than researchers initially expected. This is a significant finding for any crewed mission design. This was because a crew that arrives at another star after decades in transit with degraded cognitive function is not going to be capable of the kind of precise, complex work that establishing a presence in a new system would require. Bone marrow is similarly vulnerable. The immune system that depends on healthy bone marrow function becomes compromised under sustained cosmic ray bombardment. The crew more susceptible to infections at exactly the time when medical resources are farthest from any outside support. Here is something that adds a layer of difficulty that most discussions skip. A spacecraft traveling at a significant fraction of light speed does not simply move through the interstellar radiation environment as it exists at rest. The particles it encounters appear in the spacecraft's reference frame to be arriving with higher energies than they actually carry relative to the galaxy at large. This is a consequence of special relativity. At 20% of light speed, the relative energy of incoming particles increases. The radiation environment gets measurably worse the faster you go. Every engineering choice that pushes the spacecraft toward the speeds needed for an interstellar mission within a human lifetime also pushes the crew deeper into a radiation environment that is already at the edge of what biology can tolerate. There is no clean resolution to this. Magnetic shielding, generating a powerful magnetic field around the spacecraft to deflect incoming charged particles the way Earth's magnetosphere does, has been studied seriously. The field strengths required to deflect high-energy galactic cosmic rays are enormous. The power and mass of the systems needed to generate them are substantial. It is a possible approach, not a solved one. A spacecraft moving at 20% of light speed through the interstellar medium is not just cruising through empty space. It is slamming into particles at energies that make every second of travel a radiation exposure event. We do not currently have a material that stops that. The human body is extraordinarily good at surviving on Earth, and that is precisely the problem. Everything about human physiology was shaped by a planet with a specific gravity, a specific atmosphere, and a specific magnetic field, none of which exist aboard a spacecraft. Radiation is not the only threat waiting for a crew in deep space. It is not even the most immediate one. Long before cosmic rays accumulate to lethal doses, the body begins quietly dismantling itself in response to an environment it was never designed to handle. Gravity is not just something we live with. It is something our biology depends on in ways we are still mapping. Start with bone. In microgravity, the skeleton loses calcium at a rate of roughly 1 to 2% per month. That number sounds modest until you run it forward. An astronaut 2 years into an interstellar transit could arrive with somewhere between 25 and 40% less bone density than when they departed. That is not a manageable deficit. That is a body that fractures under ordinary mechanical stress, that cannot bear its own weight in even partial gravity, that requires years of rehabilitation under conditions that may not exist at the destination. Muscle atrophy follows the same trajectory. Without the constant low-level effort of simply holding yourself upright and moving against gravity, muscle tissue breaks down. Long-duration ISS astronauts return to Earth unable to walk unassisted, and they spent their mission doing daily exercise routines specifically designed to slow this process. The exercise helps. It does not stop the decline. A crew spending decades in transit, not months, would arrive in a state of physical deterioration that no current countermeasure has demonstrated the ability to prevent. The cardiovascular system adds another layer of difficulty. The heart is a muscle, and like any muscle, it adapts to its workload. On Earth, the heart works continuously against gravity, pushing blood upward to the brain and outward to the extremities. Remove that demand, and the heart weakens. It actually shrinks. Its output drops. Blood redistributes toward the upper body, which the cardiovascular system interprets as excess fluid volume and responds by reducing total blood volume. A crew member who has spent 30 years in microgravity transit and then steps into any gravitational field, even a fraction of Earth's, faces a cardiovascular system that can no longer maintain blood pressure adequately for upright function. The risk of fainting, organ hypoperfusion, and cardiac stress is real and serious. Then there is the problem nobody predicted clearly before astronauts started spending extended time aboard the ISS Vision. A significant fraction of long-duration astronauts have returned from orbit with measurable structural changes to their optic nerves and degraded visual acuity. The leading explanation involves intracranial fluid pressure. In microgravity, fluid that gravity would normally pull toward the lower body pools instead, around the brain and eyes. This elevated pressure appears to flatten the back of the eyeball and compress the optic nerve. For some astronauts, the changes are minor and partially reversible. For others, they are permanent. What makes this particularly unsettling is that no one has a reliable solution. Counter-pressure suits, altered fluid intake, exercise, none of these have eliminated the problem. We do not fully understand why some astronauts are affected severely and others are not. A mission lasting decades would be exposing crew members to this risk for 30 to 40 times longer than the longest missions we have studied. Immune dysregulation rounds out the picture. Spaceflight suppresses immune function in ways that are partially understood and partially mysterious. Latent viruses reactivate. The body's ability to mount responses to infections weakens. On the ISS, this is manageable because the crew is not in contact with a general population of people carrying active pathogens. On a sealed spacecraft over decades, the immune dynamics become more complicated, and any novel illness that emerges among the crew has nowhere to go and no outside medical intervention to address it. The solution that physicists and engineers consistently return to is artificial gravity. Rotate the spacecraft, and the centrifugal force acts like gravity on the crew inside the rotating section. The physics is straightforward. There is no theoretical objection. This would address bone loss, muscle atrophy, cardiovascular deconditioning, and probably the intracranial pressure problem with it. What stands between the idea and the reality is engineering mass. The rotation rate required to simulate Earth-level gravity depends on the radius of the rotating ring. The smaller the ring, the faster it has to spin. Spin too fast, and the Coriolis effect, the apparent deflection of moving objects inside a rotating frame, causes disorientation, nausea, and sensory conflict that makes the environment essentially uninhabitable. To keep rotation rates low enough for a crew to function comfortably, the radius of the rotating section needs to be on the order of several hundred meters. That is a structure roughly the length of 3 or 4 city blocks, spinning in space, integrated into a spacecraft that is already carrying propulsion systems, fuel, life support, shielding, and everything else a decades-long mission requires. Nobody has built anything like this. The engineering is probably not impossible, but the mass it adds feeds directly back into the energy problem that defines every aspect of interstellar mission design. Artificial gravity solves most of these problems in principle, but building a rotating structure large enough to be livable without making the crew dizzy from Coriolis effects means adding hundreds of meters of rotating habitat to a spacecraft that already has an impossible energy budget. Psychologists who study long-duration spaceflight have a phrase for the cluster of problems that emerges when small groups of people spend extended periods in confined, isolated environments. Behavioral health challenges, which is a clinical way of saying the mind starts coming apart. The data behind that phrase is not theoretical. NASA has tracked astronaut psychological health for decades, and the pattern that emerges from long-duration missions on the International Space Station is consistent enough to be considered reliable. Interpersonal conflict increases over time. Mood disorders develop or worsen. Cognitive performance on standardized tests declines. Sleep deteriorates. And this happens to people who were selected through one of the most rigorous screening processes in existence, supported by teams of psychologists on the ground and able to look out a window and see the Earth rotating beneath them. Remove the window, remove the support team, remove the Earth, and what you are left with is a situation that no study has ever actually simulated, because nothing on this planet comes close enough to simulate it. The closest analogues we have are Antarctic winter-over stations, where small teams spend months in isolation with no possibility of evacuation. Submarine deployments, confined habitat simulations like the Mars 500 project, where 6 volunteers spent 520 days in a facility designed to replicate a Mars mission. Every one of these studies found the same things: conflict between crew members, withdrawal and depression in individual participants, disrupted sleep, a phenomenon researchers call autonomic desynchrony, where the body's internal rhythms drift out of alignment with any external schedule. In the Mars 500 simulation, 3 of the 6 participants showed severely reduced physical activity and increased sleep duration that researchers described as hibernation-like behavior. And this was a simulation. Nobody was actually going anywhere. They could walk out if things became unbearable. This next detail is essential to grasp. On the ISS, if a crew member needs to speak with a psychologist on the ground, the message arrives in under a second. On a Mars mission, even a brief exchange takes up to 48 minutes round trip. On an interstellar journey at 20% of light speed, a message sent from the spacecraft reaches Earth years later. The reply arrives years after that. There is no conversation. There is no real-time support. There is no one to call when something goes wrong at 2 in the morning, which is when things always go wrong. The crew exists, for all practical purposes, as the only human civilization that matters. Everything that happens aboard that vessel has to be resolved by the people aboard it, with whatever knowledge and emotional resources they arrived with. That isolation compounds in a specific way over time. Early in a mission, the crew has novelty, momentum, a shared sense of purpose. Months in, those things erode. What remains is a small group of people who cannot escape each other, cannot escape the sameness of the environment, and cannot draw on any source of relief or renewal that requires being somewhere other than where they are. Researchers who study group dynamics in isolated environments describe a phenomenon called the third quarter effect, where morale and cohesion drop sharply as the crew moves past the halfway point of a mission and the end is still not close. Imagine that curve stretched across decades. The existential dimension of an interstellar journey adds a layer that no analog study can replicate. A crew leaving the solar system is not leaving temporarily. They are leaving permanently. Everyone they knew before departure will age and die before the spacecraft arrives anywhere. The civilization they launched from will have changed beyond recognition by the time any communication they send reaches it. Whatever awaits at the destination could be a barren rock with no atmosphere, which they will not know until they arrive. And there is no path home. The fuel budget, the travel time, the simple physics of the situation makes return impossible by any currently conceivable means. This is not a deployment. It is a permanent and total severance from every human context in which the crew members grew up and formed their identities. There is no established psychological profile for a person who can bear that. Psychologists can screen for resilience, emotional stability, cooperation under stress, and tolerance for monotony. What they cannot screen for is the response to a situation that has no precedent in human experience. The astronauts who go to the ISS for 6 months know with certainty that they are coming home. The knowledge that return is possible changes the psychological calculus of being away in ways that are difficult to overstate. An interstellar crew does not have that knowledge. They have only the mission, each other, and whatever internal resources they were born with and built up over their lifetimes, which will eventually run thin regardless of how carefully they were selected. Some researchers have proposed that the psychological solution is a sufficiently large crew, on the theory that social variety and meaningful relationships within a larger group might buffer the worst effects of isolation over time. Others have proposed pharmaceutical interventions, structured psychological programming, virtual reality environments rich enough to provide genuine relief. These are not unreasonable ideas. None of them have been tested under conditions that would actually allow us to evaluate whether they work for this specific challenge, because the conditions don't exist yet. The ideal crew for an interstellar mission is a group of people who can maintain psychological stability, productive cooperation, and sound decision-making for decades in a tin can with no windows, no outside communication, and no way home. And nobody has found such a group because nobody knows if one exists. The ISS is often held up as a model for long-duration human spaceflight, but it is resupplied from Earth multiple times per year, and without that supply chain, it would run out of critical consumables within months. Cargo vehicles arrive carrying food, replacement parts, medical supplies, and canisters of oxygen. Water is recycled at impressive efficiency, around 90% on the current system, but that remaining fraction has to come from somewhere. Oxygen is partially recovered from CO2 scrubbing, but regularly topped off from external supplies. The station is not a closed system. It is a very sophisticated outpost with a very short umbilical cord stretching back to Earth, and everything about its life support design assumes that cord will never be cut. Cut it, and the crew has months, not decades, months. An interstellar mission changes every number in that calculation. There is no resupply at year 3 because there is no year 3 window. There is no emergency cargo launch because any rescue mission dispatched the day you depart would take thousands of years to reach you. Every gram of food, every liter of breathable water, every cubic meter of oxygen has to either cycle endlessly through the ship's systems or be produced aboard the spacecraft itself. The engineering term for what this requires is a closed ecological life support system. The concept is straightforward. The execution, at the scale and duration required, has never been done. The basic idea is to bring a farm. Plants fix carbon dioxide and release oxygen. They produce food. Under artificial lighting, in pressurized growing chambers, a crew could theoretically sustain both its atmosphere and its caloric needs through agriculture. The problem is scale. A hectare of productive farmland, roughly the size of 2 American football fields, feeds somewhere between 5 and 10 people per year under good conditions. Getting a hectare of growing space into a spacecraft is not impossible in the abstract. Getting it into a spacecraft that also carries propulsion systems, fuel, crew quarters, medical facilities, and redundant backups for every critical system, while keeping the total mass within any range that a propulsion system could actually accelerate to interstellar velocities, is a different problem entirely. And that is before the crops fail, because they will fail. Fungal infections, lighting failures, pollination failures, soil chemistry imbalances. Agriculture on Earth fails constantly, and it does so in a planetary environment shaped by billions of years of evolution to support plant life. A hydroponic chamber aboard a spacecraft is a fragile artificial ecosystem maintained entirely by human engineering. A single pathogen that moves through the growing modules can wipe out months of food supply. There is no emergency delivery from the mainland. There is no neighboring farm. The crew either solves the problem with what it has, or it begins rationing. This is the kind of problem that cascades. Reduced caloric intake weakens the crew. A weakened crew makes more errors maintaining the systems that keep them alive. Errors in life support create new cascading failures. In engineering terms, this is a tightly coupled system with very low tolerance for perturbation, sustained over a period of 30 years. Then there is the power problem. Every system aboard a life support network requires continuous energy. Lights for the crops run day cycles measured in hundreds of watts per square meter. Water recycling requires pumps, filtration membranes, and heat exchangers. Atmospheric management, scrubbing CO2, maintaining oxygen partial pressure, controlling humidity, runs continuously. Medical equipment cannot be powered down. Climate control cannot be paused. The total power budget for keeping a crew of 12 people alive for 30 years, not counting propulsion or communication or navigation, runs into figures that require either a substantial nuclear reactor or a power source we have not built. And every system needs a backup. Not one backup, multiple. A water recycler that fails at year 12 with no replacement components and no way to manufacture them ends the mission and the crew. This means carrying redundant hardware across every critical system, which means more mass, which means more energy required to accelerate that mass, which feeds back into the propulsion problem the mission has been struggling with since the beginning. What makes this genuinely staggering is not that any single piece of the problem is unsolvable in isolation. Water recycling technology is real and improving. Closed-loop plant growth chambers have been studied seriously. Nuclear reactors small enough for spacecraft exist in concept. The problem is that all of it has to work simultaneously, reliably, for 30 years, with no outside assistance and no margin for the kind of systemic failure that even the best engineered systems eventually experience. Every calorie of food, every liter of water, every breath of oxygen for a crew spending 30 years in transit has to either be recycled with near-perfect efficiency or grown aboard the spacecraft, and doing both reliably for that long is an engineering challenge nobody has seriously attempted. Space looks empty, but it isn't. And at the speeds required for interstellar travel, that minor distinction becomes a matter of whether your spacecraft survives the journey or gets sandblasted into fragments. The interstellar medium is not a vacuum in any clean sense of the word. Between the stars, space is filled with gas atoms, mostly hydrogen and helium, along with trace amounts of heavier elements, and scattered throughout all of it are particles of dust. Microscopic grains of silicate and carbon, fragments smaller than a human hair, suspended in the dark at densities so low they are almost meaningless by any laboratory standard. Roughly 1 dust grain for every 10 cubic centimeters of interstellar space. That is extraordinarily sparse. By any measure of density you would apply on Earth, it is essentially nothing. At the speeds Voyager travels, it is nothing. Voyager 1 has been moving through the outer solar system and the near-interstellar medium for nearly 5 decades. It is still intact. At 38,000 miles per hour, dust grains bounce off or pass through the spacecraft's path so rarely and with so little energy that they pose no meaningful threat. The spacecraft was not built with interstellar dust as a serious engineering concern. Nobody had to worry about it. At 20% of the speed of light, the calculation changes completely. That same dust grain, the one that barely registers at Voyager's speed, arrives at roughly 134 million miles per hour. The kinetic energy of an object scales with the square of its velocity. You are not talking about a 5,000-fold increase in speed producing a 5,000-fold increase in impact energy. You are talking about something closer to 25 million times more energy than the same collision at Voyager's pace. A grain of sand hitting at that velocity carries the destructive force of a hand grenade. A particle the size of a single bacterium hits with the energy of a rifle round. The physics is direct. Keep this crucial point in mind. The interstellar medium between Earth and Proxima Centauri is not uniform. There are regions of higher density, molecular clouds, concentrations of gas and dust that a spacecraft passing through them at relativistic speed would encounter at a rate far above the average. A journey of 4.24 light-years takes decades, even at 20% of light speed. Decades of continuous flight through a medium that, however sparse, never runs out of particles. The erosion is not an event, it is a process. The front face of any spacecraft on that trajectory is being continuously worn away, molecule by molecule, grain by grain, for the entire duration of flight. Engineers who have studied this problem have proposed a bumper shield at the forward end of the spacecraft, a thick plate of beryllium or graphite designed to absorb impacts and ablate away gradually, sacrificing itself to protect the structure behind it. The physics of this approach is sound. Whipple shields on the International Space Station operate on a related principle, breaking up small projectiles before they reach the hull. The difference is scale and velocity. A Whipple shield handles debris at orbital speeds. An interstellar bumper faces particles arriving at a significant fraction of light speed, where the energy transfer is of a fundamentally different order. The shield would work to a degree. The problem is that the thickness required to last for decades of transit is poorly constrained because the exact distribution of particle sizes along any specific interstellar path is not well mapped. You are engineering a shield for a threat you cannot fully characterize. For a large, heavily constructed spacecraft, this might be manageable. You build the shield thick, accept the mass penalty, and replace what ablates when you can. For the breakthrough Starshot concept, the situation is far more serious. The Starshot probe is measured in grams. The sail it rides is meters wide, but thinner than a human hair, designed to be as light as physically achievable. There is no mass budget for a thick forward shield. The sail itself is the forward face. At 20% of light speed, interstellar dust does not just erode the sail, it perforates it. Studies of the Starshot concept have flagged this as one of the central unresolved problems of the entire mission design. The sail material would need to be simultaneously ultralight, highly reflective, and resistant to impacts that carry rifle bullet levels of energy. No material with all three of those properties has been developed. No material that comes close has been developed. The current candidates, graphene, thin film ceramics, offer pieces of the solution, but not the whole picture. And there is no option to steer around a hazard you cannot detect until it has already arrived. At 20% of light speed, even the thinly scattered dust of the interstellar medium hits the forward face of a spacecraft with enough energy that the material has to be either extraordinarily tough, quickly replaced, or made of something we haven't invented, and for a light sail the size of a postage stamp, those options narrow fast. The generation ship concept solves the speed problem by giving up on it entirely. Instead of trying to go fast enough for the journey to fit within a human lifetime, you accept that the journey will take centuries and design accordingly. At its core, the idea is straightforward. Build a vessel large enough to sustain a population across multiple generations. Accelerate it to somewhere between 0.1% and 1% of light speed. Velocities that advanced nuclear propulsion might actually achieve without requiring physics we don't yet understand. Then let it travel. At those speeds, a journey to the nearest star takes somewhere between 400 and 4,000 years, depending on how fast you can push the ship and which star you're aiming for. The people who board the vessel at departure will never see the destination. Neither will their children or their grandchildren. The arrival, when it finally comes, belongs to people who were born aboard the ship, lived their entire lives aboard the ship, may have only the vaguest inherited understanding of why the ship exists at all. This is where the generation ship stops being an engineering problem and becomes something stranger and harder. The physics of a slow interstellar vessel are not, in principle, beyond reach. Nuclear pulse propulsion could plausibly push a massive structure to speeds in this range. A large enough habitat, rotating for artificial gravity, could keep its population biologically functional. Closed-loop life support, while an enormous challenge, scales differently at lower speeds because you have centuries rather than decades to make it work. The ship can carry more mass without the brutal energy penalties of relativistic travel. The engineering is daunting. It is not, however, the part of the generation ship problem that has no answer. The part with no clear answer is the question of the people inside. Consider what you are actually doing when you launch a generation ship. You are sending a founding population of human beings, call it a few hundred people, or a few thousand, into a metal enclosure from which there is no exit for centuries. The people who volunteer for this understand the terms. They have made a choice. Their children have not. Every person born aboard that vessel arrives into a life they did not select, constrained by walls they cannot leave, carrying a mission they never agreed to, bound for a destination they will never reach. Whether that constitutes an ethical violation is a question philosophers have wrestled with, and there is no consensus. Some argue that the children of a generation ship are no different from children born into any culture that shapes their ions without their consent. Others argue that the degree of constraint is so extreme that it represents something categorically different from ordinary inherited circumstance. There is no good answer. There is only the question, and it gets heavier the longer you sit with it. Then there is the sociological problem. That is in some ways even harder because history gives us data on it, and the data is not encouraging. Isolated human populations, cut off from outside contact and forced to sustain themselves over centuries, do not have a reliable track record. Genetic bottlenecks narrow the gene pool. Cultural drift pulls societies away from their founding values. Social hierarchies calcify or collapse. Small groups under sustained stress develop internal conflicts that, without the pressure valve of outside contact, can become catastrophic. Island populations, remote monastic communities, isolated colonial settlements, the historical record of small groups maintaining stable, Functional civilization across long timescales without outside contact is mixed at best and alarming at worst. A generation ship population faces all of those pressures simultaneously in a closed system with no possibility of resupply or reinforcement. If the social structure breaks down in Century 2, there is no rescue. If a charismatic leader seizes control and redirects the mission towards something the original designers never intended, there is no correction from outside. If the knowledge required to maintain critical ship systems is lost across generational turnover because it wasn't written down well enough, this was because the people who understood it died without passing it on. The entire mission can fail, not from any physical catastrophe, but from the quiet erosion of institutional memory. This is why the minimum viable population question matters so much. How many people does a generation ship need to carry? The answer depends on what you're trying to preserve. For genetic diversity alone, some researchers have argued that a few hundred individuals could maintain acceptable diversity if pairings are managed carefully. Others put the number much higher. Studies on isolated populations suggest that without active genetic management, founder effects and inbreeding begin causing significant problems below populations of several thousand. For social viability, maintaining a functional division of labor across all required skills and knowledge domains pushes estimates even higher. You need doctors, engineers, biologists, psychologists, teachers, farmers. You need enough of each that losing individuals doesn't strip the ship of critical competencies. Some estimates for a genuinely robust generation ship population run into the tens of thousands. That means a vessel so large that launching it represents an undertaking on a scale humans have never attempted. And then there is the question of purpose. The original mission's founders presumably understand deeply why they are going, what they hope to find, what they intend to do when they arrive. That understanding has to survive not just the journey, but the transformation of the society making it. 800 years is longer than the entire recorded history of the United States multiplied by 4. The Catholic Church has maintained institutional continuity for longer than that, but not without schisms, reformations, and profound internal changes. Asking a ship-borne civilization to hold a course, literally and culturally, for that long, is asking something that has no clear historical precedent. A generation ship that successfully arrives at another star 800 years after departure has accomplished something remarkable. But the people who step out have no connection to the civilization that launched it, except the stories passed down through a dozen generations of people who lived and died in a metal box. The most appealing solution to the problem of keeping humans alive and sane for decades in a spacecraft is to skip the decades entirely. Put the crew to sleep and wake them up when they arrive. No psychological breakdown, no interpersonal conflict festering across 30 years in a sealed compartment. No need for a farm, a water recycling system running at perfect efficiency, or a medical bay stocked for every possible emergency across half a century. The crew climbs in, the lights go out, and the ship does the work. It is a clean solution. It is also, at present, a fictional one. The biology of freezing a living human being is not an engineering problem. It is a cellular one, and cells do not cooperate. When biological tissue cools below a certain threshold, water inside the cells begins to crystallize. Ice crystals are sharp. They puncture membranes, tear apart the internal structures of cells, and cause damage that is catastrophic at the microscopic level. By the time you reach the kind of temperatures associated with true suspended metabolism, the tissue is not dormant, it is destroyed. You can freeze a person. You cannot thaw them back out. The workaround that cryonics researchers have pursued for decades is to replace the water in cells with cryoprotectant chemicals before freezing. These compounds prevent ice crystal formation. They keep the cellular architecture intact as temperatures drop. The problem is toxicity. At the concentrations required to protect tissue during deep cooling, cryoprotectants are poisonous to the cells they are trying to preserve. You are trading one form of damage for another, and nobody has found the combination of chemicals, temperatures, and timescales that avoids both. Some organisms do this naturally. Tardigrades, those microscopic eight-legged animals that have become famous for surviving almost everything, can enter a state called cryptobiosis, essentially shutting down all metabolic activity until conditions improve. Certain insects do something similar. Wood frogs freeze solid in winter and thaw in spring. These examples get cited often in discussions of human hibernation, and they are genuinely remarkable. They are also largely irrelevant. The cellular machinery of a tardigrade or a wood frog is built for this. Mammalian cells are not. The gap between a creature that evolved cryptobiosis over hundreds of millions of years and a human crew on a spacecraft is not a gap that genetic engineering is anywhere near closing. What medicine can actually do is considerably more modest. Therapeutic hypothermia is a real clinical technique. Surgeons cool patients by a few degrees during certain heart and brain procedures to reduce metabolic demand and protect tissue from oxygen deprivation. It works, and it saves lives. The temperature reduction involved is roughly 2 to 4 degrees Celsius below normal body temperature. Metabolism slows by perhaps 5 to 10%. This is useful in a surgical context. It is not hibernation. It is the biological equivalent of turning a thermostat down slightly in a room that is still very much occupied. NASA has funded research into what scientists call torpor induction, using combinations of cooling and pharmacological agents to push mammals into a hibernation-like state for extended periods. Some animal studies have shown promising results over periods of days. Rats and other small mammals have been maintained in reduced metabolism states without apparent catastrophic damage, and the research continues. Days, though, is not years. The cellular stress of maintained torpor accumulates. Damage that is tolerable for 72 hours becomes irreversible over months, and nobody has yet demonstrated a path from one to the other that doesn't require biological mechanisms we don't know how to replicate. There is also a problem that science fiction versions of cryosleep tend to ignore entirely. A sleeping crew is not a protected crew. Cells in active metabolic states have repair mechanisms running constantly. DNA damage from radiation gets caught and corrected. Oxidative damage gets managed. A crew in torpor, with metabolism suppressed, runs those repair systems at reduced capacity, or not at all. The radiation that would already pose serious risks to an active crew becomes, if anything, more dangerous to a dormant one. Decades of cosmic ray exposure accumulating in tissue that cannot effectively repair itself is not a solved problem. It is an additional one. The romantic version of cryosleep is one of science fiction's most durable ideas, precisely because it is so elegant. It sidesteps the mess of human psychology, the complexity of life support, the brutality of the distances involved. Step in, step out, arrive. The universe, unfortunately, does not offer elegance at this scale. Cryogenic hibernation solves every psychological problem, every food and water problem, and every boredom problem all at once. And the reason it is not on any serious mission planning list is that nobody knows how to freeze a mammal and bring it back alive. Every communication challenge in the history of exploration has eventually been solved by building better technology. The challenge of communicating across interstellar distances is one that better technology cannot fix, because the fundamental limit is the speed of light. Radio waves travel at the speed of light. That is the fastest anything in the known universe can move. It means a message sent from a spacecraft near Alpha Centauri takes 4.24 years to reach Earth. The reply takes another 4.24 years to travel back. A single exchange, a question and an answer, requires more than 8 years. There is no engineering solution to this. There is no antenna design, no signal processing technique, no relay network that changes the underlying arithmetic. The speed of light is not a technology barrier. It is a law of physics. It turns mission control into something closer to a historical archive than an operational command center. Think about what that means in practice. A medical emergency aboard the spacecraft unfolds in real time. The crew has whatever knowledge and equipment they brought with them. A message describing the emergency reaches Earth 8 years after the patient is either alive or dead. The response from the best medical minds on the planet arrives 8 years after that. By the time Earth knows there was a problem, a decade and a half has passed. Every system failure, every navigational crisis, every decision that in normal spaceflight would involve dozens of engineers working through the night, all of it falls entirely on the people aboard. Earth is not a resource. Earth is a record of what used to be true. There is a second problem layered underneath the delay, and it is just as severe. A spacecraft at Alpha Centauri, broadcasting with the power of a typical satellite transmitter, produces a signal that spreads outward in all directions across 25 trillion miles of space before it reaches us. The power that arrives is not just faint, it is billions of times weaker than the already vanishingly faint signals we strain to receive from the Voyager probes. That are barely a light day away. Detecting it requires a radio telescope receiving a ray of extraordinary scale, potentially larger than anything we have built, operating continuously, pointed at precisely the right location in the sky. The spacecraft is shouting across an ocean and arriving as a whisper too quiet for any single instrument to hear. Here is something worth sitting with. An interstellar mission launched today, traveling at even an optimistic fraction of light speed, arrives at the nearest star system in roughly 20 to 40 years. The people who receive the first transmission, "We have arrived," are not the generation that watched the launch. They are not even the children of that generation. 40 years of technological change, political change, cultural change separate the moment of departure from the moment of arrival. The civilization that receives that signal may bear only a distant resemblance to the one that built the spacecraft. The institutions that funded the mission may no longer exist. The agencies that designed the communication protocols may have been replaced several times over. This is not speculation. 40 years ago, the internet did not exist in any recognizable form. The entire computational and communications infrastructure of modern civilization was built in less time than a single interstellar journey would take. The crew departing today would be sending their first transmissions home to a world they can barely imagine, using technology that their mission planners designed for a civilization that is already receding into the past. The relationship between an interstellar crew and Earth stops resembling anything in the history of human exploration and starts resembling something stranger. Early ocean voyagers left port with no communication at all. Letters moved on other ships, months behind events. But they returned. An interstellar crew does not return. The dispatches they send are not operational updates. They are historical documents by the time they arrive, describing events that happened years ago, made by people who have continued aging and deciding and living in the silence ever since. The crew of an interstellar spacecraft is not just physically cut off from Earth, they are temporally cut off, living in a present that Earth will not learn about for years. Decisions in real time that Earth can only evaluate and respond to long after the moment has passed. There is a counterintuitive argument in interstellar mission planning that suggests the worst thing you could do is launch a spacecraft to another star with today's technology, and the math behind it is hard to argue with. In 2006, a researcher named Andrew Kennedy worked through what happens when you assume propulsion technology improves at a modest, steady rate, roughly 1.4% per year. That number sounds small. Compounded across centuries, it is not small at all. Kennedy calculated that for a mission to Barnard's star, a red dwarf roughly 6 light-years away, that astronomers have studied closely for generations, the optimal departure date falls somewhere around the year 2641. Not next decade, not next century, 600 years from now. The logic is straightforward once you sit with it. A spacecraft launched today travels at whatever speed today's best propulsion can achieve. That speed is slow. The journey to Barnard's star, using the most credible near-term propulsion concepts, would take thousands of years. Meanwhile, propulsion technology continues improving. A mission launched 50 years from now travels faster. A mission launched 100 years from now travels faster still. At some point, a later ship traveling fast enough overtakes an earlier ship that left with inferior technology. The faster ship arrives first. The crew of the original mission, or their descendants, or their distant descendants, get there second, having spent centuries in transit, while the ship that passed them was still being built when they departed. This is not a theoretical edge case. It is the expected outcome if propulsion capability continues to grow. The fastest ship is always the last one launched before technology stops improving. Every mission sent before that plateau is, in some sense, sent too early. Here is what makes this genuinely strange. It means that a civilization ambitious enough to actually commit to an interstellar mission faces a dilemma with no clean resolution. Waiting makes strategic sense, but waiting assumes the future is reliable. Technological progress is not a law of physics. It is a pattern observed during a particular period of human history, under particular conditions. Kennedy's 1.4% annual improvement figure comes from averaging across an era of extraordinary scientific momentum. There is no guarantee that momentum continues. Physics may run into walls. Political will may collapse. Civilizations have stalled before, and some have ended entirely. The window for interstellar ambition is not guaranteed to stay open while you wait for the optimal departure date to arrive. Were we watching a century of progress unfold, or just a temporary burst of capability that was always going to slow down? Nobody can answer that. And that uncertainty cuts directly against the wait-and-see strategy, because the entire argument for waiting rests on an assumption about the future that nobody can actually verify. The implications for any generation that does commit to launching are uncomfortable. They would be sending people, or machines, into a journey of decades or centuries, knowing that a faster craft could be launched behind them and arrive first. The crew of that first ship might approach another star after 40 years of transit and find a probe already orbiting it, launched a decade after they left, having covered the same distance in 15 years. The first humans to reach another solar system might arrive to find their own civilization's automated scouts already there, already scanning, already transmitting back. Whether that outcome matters depends on what you think the mission is actually for. If the goal is to get information about another star system as quickly as possible, the strategic answer is to wait and send something faster when you can. If the goal is something harder to quantify, establishing a human presence beyond our solar system, crossing a threshold that changes what our species understands about itself, then the first ship carries a different kind of value that a rival order doesn't capture. What astronomers and mission planners have not found is a clear threshold at which waiting obviously becomes worse than launching. Some point to fusion propulsion as a potential inflection. If controlled fusion is achieved and scaled for spaceflight, propulsion capability might jump so sharply that waiting for it becomes clearly worthwhile, even from today. Others argue that any realistic fusion timeline is itself uncertain enough that betting on it delays a launch indefinitely. The threshold, if it exists, keeps moving. The optimal strategy is either to wait until propulsion technology plateaus, which means waiting an unknown amount of time for an event that may never happen, or to accept that the first ship you launch may be overtaken by a faster one sent decades later, and send it anyway. If you were writing the list of things that would have to change for interstellar travel to move from impossible to merely very difficult, the list would be long, and most items on it would require either fundamental physics breakthroughs or engineering achievements far beyond anything we have currently demonstrated. Start with the simplest version of the problem, not a crewed mission, not faster than light travel, just a robotic probe, something the size of a postage stamp, reaching Proxima Centauri in a human lifetime. Even that stripped-down version of the goal requires controlled fusion propulsion or a laser array drawing roughly 100 gigawatts of power. A sail material that can survive decades of interstellar dust impacts at 20% of light speed. Scientific instruments small enough to fit on a wafer, but capable of returning meaningful data. A receiving array on Earth large enough to catch a signal arriving across 4 light years at the power of a flickering candle. Each of those requirements is an unsolved engineering problem in its own right. Together, they represent a program of development that dwarfs anything humanity has attempted in the history of spaceflight. And this is before you put a single living person on board. Add a crew, and the list grows in ways that are almost discouraging to enumerate. Artificial gravity becomes necessary. This was because decades in microgravity produces physiological damage that would leave the crew unable to function on arrival. That means a rotating habitat structure hundreds of meters across. Life support has to become a genuinely closed system. Every molecule of oxygen recycled, every calorie of food either grown or perfectly conserved, every liter of water returned from waste with near-perfect efficiency for 30 years without resupply. Radiation shielding has to block galactic cosmic rays arriving from every direction, without adding so much mass that the energy budget collapses entirely. The psychological challenges have no engineering solution at all. They require a selection and support framework for small groups of people living in isolation for decades. Nothing in the history of human behavioral research tells us confidently that such a framework exists. What is strange about this list is that none of the items on it are physically impossible in the way that exceeding the speed of light is physically impossible. Artificial gravity is just rotation. Closed-loop life support is just chemistry and biology. Radiation shielding is just materials science. Each problem, examined alone, looks like something that could yield to focused research and sufficient resources. The trouble is that solving them simultaneously on a single spacecraft within an energy and mass budget that the propulsion system can actually handle is a different category of challenge from solving any one of them in isolation. The constraints fight each other. Better shielding means more mass. More mass means more energy. More energy means a larger propulsion system. A larger propulsion system means more shielding. The spiral is not infinite, but closing it to a workable design has not been done. Here is where the research currently stands. Breakthrough Starshot is the most seriously funded interstellar concept in existence. Its target is a gram-scale robotic probe, not a human mission. The dust and deceleration problems it faces remain unsolved. Fusion research at facilities like ITER and NIF is making genuine progress toward net energy gain. But the gap between a fusion reaction in a laboratory and a compact fusion engine delivering thrust to a spacecraft at 15% of light speed is an engineering chasm that nobody has bridged. The theoretical physics of warp drives and wormholes is being explored in papers and conferences, but it has produced no experimental result, no measurable prediction, no laboratory phenomenon that points toward a path forward. The math permits these things. The universe has not yet offered any indication that the math corresponds to something buildable. For faster-than-light travel, the requirements leave the domain of engineering entirely. Exotic matter with negative energy density, the substance that both the Alcubierre drive and traversable wormholes require, is not something we have failed to manufacture. It is something that may not exist in any usable form in the universe as we currently understand it. The Casimir effect produces something resembling negative energy density on a scale so small it is effectively immeasurable for engineering purposes. Whether the gap between that observation and the quantities required for a warp bubble can ever be closed is not a question physics can currently answer. It may never be answerable with the tools we have. What this all amounts to is a hierarchy of difficulty with 3 distinct levels. Robotic probes to the nearest stars in decades, conceivable with physics we understand, dependent on engineering breakthroughs that are ambitious but not obviously out of reach. Crewed missions within a human lifetime requires solving every problem the robotic case presents, plus a suite of biological and psychological challenges that have no current solutions. Faster-than-light travel requires either new physics or the discovery that exotic matter is real and accessible, neither of which is on any research roadmap in a concrete form. The 25 trillion mile gap is real. It is enormous. Every serious attempt to close it so far has arrived at the same conclusion. The universe does not make this easy. Whether it makes it possible at all depends on answers that nobody has yet.